NASA today finally having a live stream event which it says are new images trying to answer that question. Is it a gigantic icy rock or possible sign of an alien intelligence? NASA has just released the first wave of new data on the interstellar visitor known as 3I Atlas, and the reaction across the scientific community is immediate. After weeks of anticipation, the agency finally unveiled a set of fresh images and spectrographic readings that were expected to clarify one of the most confusing objects to enter the inner solar system in recent years. Instead, the material has raised even more questions. The new frames appear faint, heavily processed, and strikingly similar to earlier observations from Hubble, Swift, and the James Webb Space Telescope. The public was told to expect insight. What arrived was a collection of blurred shapes and ultraviolet signatures that confirm only one thing. The object is there, active, and shedding hydrogen. Everything else remains unresolved. The announcement emphasized that more data are still being downloaded through the Deep Space Network, but several anomalies associated with 3I Atlas were not addressed. Observers expected clarity on the shifting tail, the puzzling jet behavior, and the unusually large mass estimate. None of those topics appeared in the briefing. What NASA presented today may be scientifically accurate, but it leaves the central mystery untouched. A rare interstellar object is passing through the inner solar system right now, and the new information only deepens the sense that something about it does not behave like a typical comet. In the hours following the announcement, researchers around the world began dissecting every frame NASA published, but one theme kept emerging. The material does not match the scale of the expectations. Scientists had hoped this release would finally illuminate the nature of the object that has been confounding observatories since midsummer. Instead, what appeared on screen looked almost deliberately cautious. The images from the Mars-orbiting MAVEN spacecraft show a compact ultraviolet signature, little more than a concentrated blob of hydrogen against a wide field of interplanetary gas. The Swift ultraviolet telescope contributed additional detections, but they follow the same pattern. The comet is active, but its behavior does not align cleanly with known models. Even the carefully processed views from SOHO, captured from more than twice the Earth-Sun distance, underscore this uncertainty. The object is visible, but its structure remains indistinct, as if resisting straightforward interpretation. During the briefing, NASA emphasized calibration steps, data pipelines, and the need for peer review before any scientific conclusions can be drawn. That caution is understandable, yet it highlights an unusual tension. 3I Atlas is only the third confirmed interstellar object ever observed passing through the solar system, and its anomalies have been documented for months. The shifting tail, the tightly collimated jets, the unexpected mass estimates, and the unlikely alignment of its trajectory with the planetary plane. None of these features were confronted directly in today's release. Instead, the agency presented a conservative summary that frames the comet as rare but fundamentally familiar. That approach may be scientifically responsible, but it does little to address the central question following this object. Why does it behave so differently from everything astronomers are used to seeing? The briefing opened with a sequence of ultraviolet observations collected from multiple spacecraft, each offering a narrow glimpse at the interstellar object as it moved deeper into the inner solar system. The first dataset came from MAVEN, which captured a distinct hydrogen emission, forming a compact, bright patch on the instrument's left band. To its right, two wider signatures showed hydrogen from the Martian atmosphere and the surrounding interplanetary medium. This contrast made one fact clear: the emission tied to 3I Atlas is real, localized, and active. It confirms material is escaping from the nucleus, even though the size of that nucleus remains unresolved. Next, the Swift ultraviolet telescope contributed its own readings. These confirmed water-related activity, but in a subdued and tightly concentrated pattern, rather than the broad dispersal expected from a typical comet of this scale. NASA noted that these measurements will help determine the object's water production rate as it continues to warm. Still, the data stopped short of explaining the asymmetric outgassing that earlier amateur images suggested. The James Webb Space Telescope provided an additional layer of spectroscopy, offering chemical hints without a definitive composition breakdown. Webb's earlier detections of unusual ratios, especially the imbalance between hydrogen and heavier volatiles, were mentioned only briefly, framed as part of an ongoing effort to calibrate and combine datasets. Finally, NASA displayed a remarkable set of processed frames from SOHO. Captured at a distance of more than twice the Earth-Sun separation, the object appeared as a faint moving point, detectable only after detailed stacking of consecutive images. The agency highlighted this as evidence of how difficult the target remains to observe, given its position near the Sun and the glare that overwhelms most instruments. Even so, the detection confirms that 3I Atlas remained active after passing close to Mars and continued to shed material during its approach toward perihelion. Throughout the presentation, NASA reiterated that these images represent only the first stage of analysis. More data are still being downlinked through the Deep Space Network, and several instrument teams have not yet finished their internal calibrations. For now, the material shown today establishes the comet's presence, its hydrogen activity, and its survival past perihelion, but leaves most of its deeper characteristics unaddressed. While the briefing delivered a clean overview of hydrogen activity and ultraviolet signatures, several of the most controversial scientific anomalies associated with 3I Atlas were not addressed at all. The first omission concerns the object's extraordinary mass estimate. Based on early measurements of its diameter and reflected brightness, researchers calculated that 3I Atlas could be up to 1,000,000 times heavier than Oumuamua and nearly 1,000 times heavier than Borisov. For an interstellar object, that scale alone challenges current models of how solid bodies form and travel through interstellar space. Yet the briefing made no reference to those estimates, nor to the implications they carry for understanding the population of objects drifting between stars. Another absence involved the unusual alignment of its inbound trajectory. Most interstellar visitors are statistically expected to arrive from random angles relative to the solar system's planetary plane. Instead, 3I Atlas approached almost perfectly along that plane, a coincidence so precise that it enabled simultaneous observation by multiple NASA instruments. Many astronomers consider such an alignment unlikely without an underlying cause, but the briefing glossed over this entirely. A third omission concerned the jet behavior observed in late summer. Amateur astronomers documented up to 7 tightly collimated jets extending nearly 1,000,000 kilometers from the nucleus. What makes this remarkable is the rotation period, estimated at roughly 16 hours. If correct, that rotation should twist, bend, or smear the jets as the object spins. Instead, the jets appeared stable and narrow, an effect that remains unexplained. Despite its scientific relevance, this anomaly did not appear in the livestream content. The briefing also avoided discussing the shifting tail pattern that evolved in midsummer and early autumn. The appearance of an anti-tail, material seemingly pointing toward the sun, followed by a conventional tail appearing briefly and then disappearing again, remains one of the most debated features of the object. These transitions occurred too quickly and cleanly to be fully consistent with standard comet dynamics, but no mention of them was made. For many researchers, these omissions highlight a broader issue. The new material confirms activity, but does not engage with the deeper puzzles that made 3I Atlas a scientific outlier in the first place. Without confronting those features directly, today's release clarifies the object's presence, not its nature. Among all the features recorded over the past several months, the evolution of the tail remains one of the most persistent anomalies tied to 3I Atlas. In July and August, telescopes documented a pronounced anti-tail, a stream of material appearing to point directly toward the sun rather than away from it. This configuration can occur under specific geometric conditions, but the clarity and stability of the structure surprised observers. It held its shape for an extended period, showing none of the distortion or broadening expected from solar wind variations during that time. By early September, the geometry shifted. A conventional tail briefly emerged, extending outward in a narrow line before fading again. Observers tracked it for only a short interval before sunlight interference made the object inaccessible. When visibility resumed after the perihelion passage, the situation became more unusual. Both an anti-tail and a traditional tail appeared in newly processed images, indicating simultaneous streams of material moving in different directions relative to the Sun. Complicating matters further were reports of tightly collimated jets captured by amateur astronomers. In one widely shared observation, a single jet extended nearly 1,000,000 kilometers from the nucleus, holding a straight, thin line over multiple frames. This behavior clashes with the estimated 16-hour rotation period. If the object were spinning at that rate, the jets should twist as the surface orientation changes. Instead, they remained aligned, suggesting a form of ejection that does not conform to typical cometary physics. NASA's briefing acknowledged ongoing analyses of outgassing, but did not reference these structural inconsistencies. The presence of alternating tails, the brief appearance and disappearance of the conventional tail, and the lack of rotational smearing in the jets all indicate that 3I Atlas is responding to solar forces in a way that standard models struggle to capture. For many researchers, the tail is not simply a visual feature. It is one of the clearest markers that this interstellar object behaves differently from anything routinely observed in the solar system. The deeper researchers examine 3I Atlas, the more its behavior diverges from expectations for any natural comet entering the inner solar system. The object's estimated mass remains one of the strongest points of confusion. Early size calculations, based on its reflected brightness and the persistence of its activity, suggest a nucleus far larger than the two previously known interstellar objects. That scale introduces a major problem. Interstellar space does not easily produce or preserve bodies of that size. If it did, the solar system should have encountered similar objects long before now. The absence of such a population raises immediate questions about how 3I Atlas formed and why it managed to survive an interstellar journey that would normally erode or fragment a body of comparable mass. Its rotational behavior adds another layer of uncertainty. A rotation period, estimated at roughly 16 hours, should produce clear patterns in the distribution of dust and gas. Instead, the emissions observed so far show a level of stability inconsistent with a spinning nucleus. The jets remain narrow and coherent, and the shifts in activity do not match the timing expected from sunlight heating different regions of the surface. This disconnect between rotation and outgassing challenges the idea that standard sublimation is responsible for the observed features. Chemical measurements complicate the picture further. Ultraviolet spectrographs detect hydrogen release, but the ratio of hydrogen to heavier volatiles does not align neatly with typical comet chemistry. The activity appears both concentrated and irregular, as if the object's surface composition varies more dramatically than standard models allow. The faint but clear signals captured by Swift, Maven, and Webb confirm ongoing activity. Yet none of the instruments reveal a consistent pattern that explains how the material is escaping or why it behaves as it does near the Sun. Even the brightness curve defies expectations. Most comets brighten steadily as they approach perihelion, but 3I Atlas has shown uneven changes that do not correspond cleanly with its distance from the Sun. That inconsistency complicates attempts to model its size or surface reflectivity with any confidence. Without reliable brightness behavior, mass estimates remain uncertain, and researchers are left with calculations that point toward an object far more massive than theory would predict. Taken together, these issues create a rare scientific scenario, an interstellar object that obeys some basic cometary principles, but violates enough of them to resist straightforward classification. The puzzles do not imply anything extraordinary by default, but they do indicate that the standard frameworks used to understand comets inside the solar system may be insufficient for describing a visitor that formed under entirely different conditions. The new observations reveal several important truths about 3I Atlas, but none of them resolve the deeper questions that have followed the object for months. The ultraviolet signatures captured by Maven provide the clearest confirmation that the nucleus is actively releasing hydrogen. This activity indicates the presence of water-bearing material beneath the surface, reacting to solar heating as the object moves inward. However, the compact shape of the emission suggests a tightly confined region of activity rather than the broad, diffuse release expected from a large comet. It identifies the presence of water, yet not the mechanism behind its uneven escape. The swift detections offer another crucial piece of evidence. The measurements align with a water production rate that is neither unusually high nor unusually low for a body near this distance from the Sun. That suggests 3I Atlas is losing material, but the data do not explain why the activity appears asymmetric or why the jets remain so narrow. Swift confirms the chemistry but does not clarify the physics driving it. SOHO's processed images highlight a different aspect of the story. The fact that the object was visible from more than twice the Earth-Sun distance, despite its faintness, indicates that 3I Atlas continues releasing enough material to register against solar glare. This confirms its persistence after perihelion, but it does not reveal anything about the size or structure of the nucleus. The stacked images simply establish that the object remains intact and active. Together, these datasets help define the boundaries of what is known. 3I Atlas is shedding hydrogen. It contains water-bearing material. It remains stable after perihelion, and it continues to reflect enough light to be tracked at great distances. Yet none of these facts address the anomalies that make the object so unusual. The data confirm activity, not identity. They describe what the object is doing, but not why it behaves in ways that conflict with established comet dynamics. This leaves researchers in an early stage of analysis, where the emphasis is placed on calibration, cross-referencing, and caution. The new images provide a starting point, not a conclusion. They refine the observation timeline, but do not change the fundamental truth. The nature of 3I Atlas is still far from understood. Despite the new ultraviolet images and the carefully processed frames released today, the central mysteries surrounding 3I Atlas remain unresolved. The briefing confirmed activity, but left some of the most critical scientific questions untouched. Foremost among them is the issue of scale. If early estimates are correct, and the object truly possesses a mass far beyond that of the two previous interstellar visitors, then its existence challenges current understanding of how large bodies form and survive in the space between stars. The briefing made no attempt to explain why an object of such size would appear only now, or why no comparable interstellar travelers have been detected before. Another unanswered question involves the object's improbable trajectory. 3I Atlas entered the solar system almost perfectly aligned with the planetary plane, a coincidence that dramatically increased its visibility to Earth-based and space-based observatories. The likelihood of such an alignment occurring by chance is low, yet the briefing declined to address whether this orientation holds deeper implications or represents an unusual dynamical history. The stability of the jets remains another unresolved puzzle. Observations from midsummer showed narrow, sharply defined jets that did not twist or bend as a 16-hour rotation period would predict. Without a clear explanation, the behavior points to a mechanism that differs from standard cometary outgassing. The briefing acknowledged active hydrogen release, but did not confront the inconsistencies in the jet structure or their persistence over time. Even the chemical profile raises open questions. The hydrogen release confirms water-bearing material, yet the ratio of hydrogen to heavier volatiles remains atypical. The data available so far do not identify whether this pattern reflects an unusual internal composition or a surface layered by interstellar weathering over millions of years. Ultimately, the material released today narrows the observation timeline but expands the conceptual gap. 3I Atlas is active, real, and scientifically significant, but the features that made it an anomaly in the first place remain without clear interpretation. Until additional datasets arrive and deeper analysis begins, the object stands at the center of a growing list of unresolved scientific questions. The release of these new observations marks an important step, but it is far from the final chapter in understanding 3I Atlas. The data confirm that the object survived perihelion, continues to shed hydrogen, and remains bright enough for long-range detection. Yet the anomalies that first drew global attention, the unusual mass estimates, the unexpected trajectory, the irregular outgassing, and the shifting tail, remain without clear explanation. For now, researchers are still in the earliest phase of sorting through calibration files, cross-checking spectra, and building models that can withstand peer review. The next stage will depend on additional downloads from the Deep Space Network and continued monitoring from ground-based telescopes as the object moves into a more favorable observing position in December. These upcoming datasets may clarify the size of the nucleus, refine the rotation period, or reveal chemical signatures that have not yet been resolved. They may also raise new questions, as interstellar objects often defy assumptions shaped by solar system comets. As it stands, 3I Atlas remains a rare visitor, moving through the inner solar system with a set of behaviors that resist familiar explanations. The information released today brings the scientific community closer to understanding its nature, but the path to a complete answer is still ahead. The coming weeks will determine whether this interstellar object fits within existing theories or forces those theories to change. In that sense, the story of 3I Atlas is not concluding. It is just beginning.